Okay, guys, your second section of this week class is about NMR, nuclear magnetic resonance spectroscopy. So NMR spectroscopy is the most commonly used technique for determining the structure of an organic compound, useful for identifying the hydrocarbon skeleton to which the functional group is attached. So usually we have two common types of NMR, proton NMR and carbon NMR. In proton NMR, you can find some qualitative and quantitative characterization of the different types of hydrogen in the molecule. And in carbon NMR, you can identify the carbon of the skeleton. A spin charge such as the nucleus of proton or carbon generates a magnetic field. The magnetic field generated by a nucleus of a positive spin is opposite in direction from that generated by the nucleus of negative spin. So the distribution of nuclear spin is random, as you can hear, for example, in this figure, in the absence of an external magnetic field. But when we apply an external magnetic field, so they will be aligned parallel or anti-parallel to applied field. Parallel or anti-parallel. So the frequency of absorbed electromagnetic radiation is proportional to the energy difference between two nuclear spin states, which is proportional to the applied magnetic field. So NMR is concerned with change in the direction of the spin orientation, called nuclear magnetic resonance, as a result of the absorption of radiofrequency radiation. The frequency of absorbed electromagnetic radiation is different for different elements and for different isotopes of the same element. The frequency of absorbed electromagnetic radiation for a particular nucleus, such as proton and carbon, depends on the molecular environment of the nucleus. If all the protons were exposed to the same magnetic field, they would absorb at the same frequency. Actually, when a molecule is subjected to a magnetic field, the bonding electrons circulate in such a way as to generate additional weak magnetic field of their own. In general, this new magnetic field opposed the large fixed magnetic field, which had the effect of partially shielding the underlying nucleus. The greater the shielding, the lower the frequency required to produce resonance. So, about the chemical shift. Chemical shift is a measure of the degree to which a nucleus in a molecule is shielded. Proton is different environments are shielded to greater or lesser degrees. They have different chemical shift. So we use TMS as this reference, and its chemical shift will be 0. So here, for example, the TMS chemical shift is almost 0. So about the shielding, well, for example, when we have an electronegative atom in our structure, so the shielding will be less, and so the chemical shift will be higher. For example, when we have fluor atom, which is a strong electronegative atom, so the shielding will be higher, and the chemical shift will be the shielding will be less, and so the chemical shift will be higher. So in addition to having an electronegative atom, so you can have several electronegative atoms. When the electronegative atoms amount is increasing, so the shielding will less and the chemical shift will be higher. In addition to the electronegative atom, having electronegative atom or not having the electronegative atom in the structure, the hybridization of the center atom, for example here carbon, will affect on the shielding. sp2 hybridization will have less shielding in comparison to the sp3 hybridization. So that's why when the hydrogen is bonded to a carbon with sp2 hybridization, the chemical shift will be higher. So we can derive several types of information from proton NMR. For example, from the number of signals, we can see how many different types of hydrogen we have in the molecule. From the position of signal, we can know how many different types of hydrogen we have in the structure. Relative area under signal can give us some information about how many hydrogen of each type we have in this in the structure. And a splitting pattern can give us some information about how many neighboring hydrogen we have in the structure. So, for example, in toluene here, we have two different hydrogen. This one and the hydrogen in the benzene ring. So that's why we have two peaks in our NMR spectrum. Or here you can see, for example, here we have just a single type of hydrogen. Here we have the single type. All of these hydrogen are same in environment, or even here. But here we have two different type of hydrogen, these methyl groups and the hydrogen on the benzene. Here we have same. All of these hydrogen from these methyl groups are same. Their position to the electronegative atom is same. They are same here, but we have two different groups. For example, here in rather to the position of boron atom, we have two different. These two hydrogen are closer. These three hydrogen are little far. So we have two different. Or here we have two different. These two methyl have same position to the color, but this single hydrogen is different. And here we have three different types of hydrogen based on the distance to the boron atom. So here we have four different. You can just compare their position to the boron atom. Here we have three different. You can two different. You can compare their position to the color atom. And here we have three different types of hydrogen based on their position to the color atom. So about the integration, we can, based on the integration, we can know how many hydrogen of each type we have. For example, here the type A is 3 hydrogen, type B is 2 hydrogen, type 3 is 2 hydrogen. So the intensity of their peak will be decreased from A to C. The peak of the A will be stronger, and same for this compound. For A type we have 6, so the peak will be stronger. However, for B we have just a single hydrogen, so the peak will be smaller. The ratio will be 6 to 1. So for example, here we have 12 hydrogen, so we will have a single strong peak. Over here we will for A type we will have 6, but for B type we will have 4, so the ratio of the two peaks will be 6 to 4. Or here I can give you another example. So for A type we will have 6, so it will be a sharp peak, but for the B type we will have just a single hydrogen, so it will be a smaller, much smaller peak. And same to, for example, this compound, which we have 3 types of the hydrogen. So for A we will have a peak in its integration relation to 3 hydrogen. For C we will have a peak related to 4 hydrogen, and for B we will have a peak related to 2 hydrogen. So the bigger peak will be related to hydrogen type C, and the medium peak will be related to A based on the intensity of the peak, and the smallest peak will be the related to the hydrogen type B. So position of the signals and in fact chemical shift of there is based on the environment of them. For example, hydrogen which is bonded to carbon which has a color atom on it, so it will be appear between 3 to 4, or when that electronegative atom is boron, so the hydrogen bond will be appear in hydrogen. The NMR bond of that hydrogen will appear between 2.5 to 4. So as you can see here in this graph, so in different range, you will see, for example, here for alcohol when we have a OH group on the carbon, so the peak of that types of hydrogen will appear between 3 to 4 in this area. So here in this graph, you can see the different range of each hydrogen based on the neighbor of the hydrogen in different chemical shifts. So when the protons are not structurally equivalent, a phenomenon called splitting is observed. So the more common splitting patterns are single, doublet, triplet, quartet, and quintuplet or multiplex. Splitting higher than this is usually called a multiplet. So splitting pattern follow the n+1 rule. When you have n neighbor hydrogen, so splitting will be n+1. So for example, here this hydrogen has no hydrogen neighbor. Neighbor defines as 3 bonds away. 1, 2, 3. 1, 2, 3. 1, 2, 3. So you can see 3 bonds away, there is no hydrogen to be called as neighbor of this hydrogen. That's why this hydrogen will have a single bond. But for this hydrogen, 1, 2, 3, will have another hydrogen, one hydrogen. This neighbor hydrogen will cause a double splitting pattern for this hydrogen. But here we have 2 neighbor hydrogen, 1, 2, 3, 1, 2, 3. That's why n+1, 2 plus 1, 3, triple pattern. And for this one, we have 3. That's why we have a quartet pattern, 3 plus 1, 4. So splitting pattern, in general, an equivalent neighboring hydrogen will split a proton signal into an n+1 Pascal pattern. So when there is no neighboring hydrogen, so the peak will be the single pattern. But when we have 1, it will be double. When we have 2 neighbor hydrogen, it will be triple. When we have 3 neighbor hydrogen, it will be quartet. And when we have 4 neighbor hydrogen, so the pattern will be a quintet. N must be equivalent neighboring hydrogen to give rise to a Pascal splitting pattern. If the neighbor are not equivalent, then you will see a complex pattern. OH of the OH group, this hydrogen from this OH group, from the alcohol group, usually doesn't split neighboring hydrogen signal, nor is it split. Normally a single of integration, 1 between 1 to 5.5. I will show you in some examples. So let's consider some NMR peak of some compounds. For example, here in cyclohexane, you can see, so even from the structure, we can see that we have 12 same hydrogen. So that's why we have a sharp peak and a single sharp peak in the NMR spectrum. So this sharp peak and its intensity is related to this number 12. That's why it's a sharp peak. And so we have just a single type of hydrogen. That's why we have a single peak. So in this compound, we have single type again, single type, and 12 hydrogen. So just a single sharp peak. In benzene, we have a single and 6 hydrogen. So a single sharp peak, but the chemical shift is different based on the hybridization. Here is sp2, but before that, for those previous two examples, the hybridization was sp3. So for this one, we have two different peaks. The first one, the A type, has 6. You can see it's a larger peak. The intensity is higher. And for the second one, the B type, we have 4 hydrogen. That's why it's a little smaller. So for tertiary butyl bromide, so we have just a single type of hydrogen. That's why we have a single peak, and it's related to 9 hydrogen. So for ethyl bromide, we have two different group of hydrogen. The first group is A. So A has 2 hydrogen as neighbor. So it's triple. You can see 1, 2, 3. But for type B, which is closer to boron atom, that's why the shielding is less and the chemical shift is higher. So we have 3 neighbor hydrogen. That's why it's a quartet, 1, 2, 3, 4. But for this compound, so we have 3 different types of hydrogen here. A type will be triple because its neighbor is 2 hydrogen, triple. The B type will be complex because it has 5 hydrogen, and these 5 hydrogen are not equivalent because these 2 hydrogen are close to boron, but these 3 hydrogen are far from the boron. And these 2 hydrogens, the type C, which will have a triple bond. You can see 1, 2, 3. And its chemical shift is highest one because it's so close to the electronegative atom. So here again we have 2 different hydrogen. That's why we have 2 different two different peaks in the NMR spectrum. So the first one is related to 6 hydrogen. That's why it's so strong. And the second one, which is closer to the electronegative atom, the color, and that's why the chemical shift is higher, the shielding, because the shielding is less. And so that's the smaller peak because it's just related to 1 hydrogen. So in this example, we have 4 different types of hydrogen based on their position to the boron atom. So the first one is these 3 hydrogen. These 3 hydrogen will be triple because they have 2 neighbor hydrogen. The second group with these 3 hydrogen, they are different because the distance between A to boron atom and B to boron atom is different. So this B group, these 3 hydrogen, will be doubled because they have just a single neighbor hydrogen. The C group will be complex because they are neighbor to 4 hydrogen which are not equivalent based on their position to the boron. This single hydrogen is so close to boron, however, the 3 hydrogen are far away. And the D group, which is that hydrogen is on the carbon, is bonding to the carbon, which is directly bound to the boron. So it is neighboring to 5 hydrogen, which are not equivalent. So that's why the peak of this D is complex. Another example here. We have 3 different types of the hydrogen. That's why we have 3 peaks here, but all of them are single because they have no neighbor hydrogen. So another one, ethanol. So as I've mentioned about the alcohol group, OH group, it will be a single and it will not split the neighbor hydrogens. But we have 2 another types of hydrogen based on the position to the OH group. So the first 3 hydrogen will be triple because of these 2 neighbor hydrogen, and these 2 hydrogen will be quartet because of these 3 hydrogen. So for this example, we have 3 different hydrogen. So the first type is type A. So we have six hydrogen for type A, and they will be triple because they are neighbor to two hydrogen. And type B, which will be quartet because they are neighbor to these three hydrogen. And we will have a singlet from this benzyl group. They are four hydrogen, 1, 2, 3, 4. They have no neighbor. That's why uh, it will be singlet, and you can see that the chemical shift is so higher than in comparison to the two other types because it's sp2. So here another example, we have four different types of hydrogen. Again, an alcohol group, it will be a singlet, type C, a single hydrogen, and the peak will be singlet. But for these three hydrogen, the peak will be triplet because these two neighbor hydrogen. And for the type D, again, it will be triplet because of these type B, these two hydrogen, which is neighbor to this type D. So in addition to proton NMR, we have carbon NMR. So for carbon NMR, for number of signal, you can know how many different type of carbon you have in the structure. And from splitting, you can know number of hydrogen on each carbon. In addition, from chemical shift, you can know hybridization of carbon, sp, sp2, or sp3. And from the chemical shift, you can recognize environment of the carbon. So, for example, here in this compound, we have four different carbons based on their position to, for example, to the boron atom, and you can see four different peaks in this carbon NMR spectrum. Okay, guys, that was your today and in fact your last class presentation. Good luck.